So welcome everybody to the third colloquium in this summer series. Last week we were hearing about individual stellar evolution and the effects of environment of that on parsec to 100 parsec scales. We're not actually, as far as I know, going to change the scale, but instead of looking at one star, we're going to probably be looking at God knows how many stars, many stars, and that's in the centers of galaxies. And we're very fortunate and honored to have as a speaker today Professor Susanne Aalto from Chalmers University in Sweden, who is specialized in observing these things in ever increasing ingenious ways over the last 20 or more years. Susanne did her PhD also at Chalmers in 1994 on molecular clouds in starburst galaxies. And she followed that by 2 postdocs in the USA, in Steward Observatory in Arizona and then Caltech. Before returning to Chalmers, she became a full chaired professor in 2013. And in 2017 to 2020, she was actually the head of the Division of Astronomy and Plasma Physics. And then looks like she did that job very well, because last year she took over the leadership of the whole university faculty, a very large range of subjects. She has been the recipient of many honors and awards. Just to mention a couple of them, she had last year the Vandenberg grant to look at cosmic dust, which is going to be, I think, something she's going to tell us quite a lot about in this colloquium. And a couple of years ago, actually 2018, she received an ERC advanced grant to explore the hidden dusty nuclei of galaxies. And this is the subject of her colloquium. So without any further ado, I'd like to welcome again Susanne, and we're very interested to hear all about this intriguing topic. Thank you.
Great, thank you so much for this nice introduction, Richard. I wish I could say I'm so happy to be here, but you know what I mean.
Yes.
We're all lurking at home. I am currently in my living room, actually, and I just wanted to warn you, just as I did for Richard, that an angry cat may appear out of the blue, being very annoyed that I'm not giving her my attention. So don't be alarmed if you see a hairy paw. It's not mine, if it appears in front of the screen. So what I want to talk about today is thick as thieves, unveiling the most compact and obscure nuclei. And this is work that I've been doing. It's sort of like, as Richard was alluding to, I've sort of been slowly sort of gliding into towards these extreme objects the past few years, as we've just been discovering these extremely dust enshrouded objects. So today what I wanted to talk about is basically this. Why do we care about dusty nuclei? It just gets in the way. Why do we care about these objects? And then I'm going to move on to talk about the tori and give an example of NGC1068 just very briefly before we move into the compact obscure nuclei, the CONs. I'll give you some examples and show you how we can study them with Alma at this incredible spatial resolution of, now we're now talking about milliarcseconds that we can do with Alma. And then I'm going to move on to talk about dusty feedback in terms of AGN and starburst feedback, and I'll focus on one of my pet galaxies, NGC1068, and we'll go to some conclusions. Now you'll scream if you can't hear me. I realize that maybe that's a contradiction in terms. We'll see how it goes. So, dusty growth. So we have luminous and ultraluminous infrared galaxies. I'm sure many of you are familiar with them. They have luminosities in excess of 10 to the 11 solar luminosities. And they're very dusty objects. They're often interacting, and they are fundamental to our understanding of galaxy evolution, because in these objects, the evolution, the growth of the galaxies are basically on speed. They're going through a phase of very fast evolution. So we're interested in them as building blocks, if you like, of the structures also of the universe. These objects have particularly, some of them have particularly embedded nuclei that we're going to see, where the evolution is going really fast, and we're talking maybe fractions of mega years even. Obscured activity also occur in less extreme objects. We have obscured AGNs, and we know now that most of the active galactic nuclei, the growing supermassive black holes, are obscured in the universe. And we want to study the shape and structure of the obscuring torus, which is linked to the feeding of the black hole, the SMBHs, and which in turn then lead to feedback that we can detect in the forms of outflows, for example, mechanical feedback, but also radiative feedback that heats and dissociates the surrounding gas. We want to understand how these dusty objects function and work because, of course, we want to understand how galaxies grow and evolve, but we also want to understand how the host galaxies, the starbursts, are connected to the growth of the black holes. Furthermore, we also want to understand how the small-scale obscuration, often seen in X-ray obscurations, are linked to the larger scales of obscuration we see on 10 or 100 parsecs, and even onto larger scales. And also the binding, connecting theme of this is also that all this nuclear activity will drive mechanical feedback in the form of molecular winds, jets, and outflows. Now, if we want to study obscured activity, of course, one of the most classic approaches will be to go to the mid-infrared and look at, for example, pHs, polycyclic aromatic hydrocarbons, and look at silicate absorption structures, and also to look at the mid-infrared slope. And we can use these tracers to probe obscuration. We see it, for example, in the form of 9.7 micron silicate absorption feature, very deep absorption features that we can see in the infrared spectrum, and also water features that we can detect in the mid-infrared. So we can use these tracers to probe evolution, for example, connected to merger stage. We can look for effects of impact on radiation in something called PDRs, photon-dominated regions, where the radiation is dominating the structure of the gas. And we can look at ionization rates and grain sizes, compactness and temperatures. We can use this mid-infrared study to reveal the buried AGNs, for example. Moving on to longer wavelengths, we can use the far infrared to reveal embedded star formation at 50. Now we're to 5200 microns in wavelength, and we can use these probes to trace star formation laws. We can get spectral energy distributions, which of course they peak here. So this is the region where many of these infrared luminous galaxies have their peak output. So this is an extremely important region to study, and it's been done so, for example, with the Herschel Space Telescope. And here we can also start to access some molecules. We can get highly excited HCN, for example, water, OH, and various molecular ions. And we use them to probe the chemistry and the excitation of the gas, to see effects of dust grain processing, and also to see effects of inflow and outflow. So this is an extremely important region as well to probe behind the obscuring veils that stop us prevent us from seeing into these structures at optical wavelengths. But perhaps some of the most efficient tools to really probe behind the dusty veils is to use molecules. Now, I'm an extragalactic astronomer, and up until quite recently, we have mostly used this molecule, CO, and particularly the low J transitions. Now, this is a molecule, you see it here, which we can use to trace low density molecular gas. And for me, low density is a couple of hundred per cubic centimeter. We also, some decades ago, got access to the polar molecules, HCN and HCO+, for example, to probe the dense molecular gas. And now we're up 2 orders of magnitude in density, so 10 to the 4 per cubic centimeter. And we use these molecules to probe dense gas and star formation, and also close to AGNs. And also the final stages before star formation is when the gas gets this dense. So putting these two tools together gave us a very nice way of probing the properties of the molecular gas and the star formation. So the stage is right before star formation in external galaxies. And of course, we can also use these probes to trace the dynamics of the nuclear gas. And this is what we're going to do a bit more today. The reason why we do this is because what we really want to get at is, of course, the cold H2, the cold molecular hydrogen. But this is a quote-unquote silent molecule. So it doesn't emit while it is cold. So we have to, because it lacks a permanent dipole moment. So we need to use tracer molecules such as these to probe the molecular gas, that is the phase right before star formation or close to the feeding of the black hole. Of course, this field has exploded and evolved with the advent of instruments such as NOEMA, NOEMA, and Alma, of course. And now we can use molecules to diagnose star formation and AGN activity in a variety of ways, with a huge variety of tools. We can, for example, as I said before, study gas distribution dynamics, dynamical masses, look for non-circular motions out and inflows. And this has become an extremely important tool to understand the feedback processes in galaxies. And we see, as we shall see soon, molecules carry with them a lot of the momentum in many of these outflows. This is quite fairly recent discovery. We can probe physical conditions. We can get temperatures. We can, for example, use formaldehyde to directly measure the temperature of the gas. And we can get the density through combining several of these traces together. We can also see how the radiative feedback impacts the excitation of the molecules and directly probe dust-embedded sources through this way. On top of all this, we can use astrochemistry, which is extragalactically a fairly new field, because it's just in the past, I'd say 10, 15 years that we've really had the tools to do this effectively. Using astrochemistry, we can probe, for example, the impact of an AGN versus a starburst. This is particularly important when the activity is dust embedded and we cannot use optical tools, for example, to determine what's going on in there. We can study outflow mechanisms, impacts of dynamics on the interstellar medium in itself. We can even probe stellar enrichment through using isotopologues and look at dust gas processes. And there's a very ongoing effort, currently ongoing effort, to benchmark some key diagnostic molecular species and lines. And I want to particularly mention this one here. This one is particularly famous in extragalactic studies. What we have on this plot here is the HCN. So remember, the HCN is tracing dense gas. Over CO, that's tracing lower density gas. So one could imagine that using this line ratio will give us an idea of the dense gas content. And then we use the ratio between HCN to HCO+. We're both tracing dense gas, but different environments. And there is a suggestion by Kotaro Kono and his team that using this combination of line ratio could help us distinguish between AGNs and starbursts in obscured systems. Now, there's been a lot of studies of this, and I'm not going to spend much time during this talk, but this is an important line ratio that is currently being explored and tested and benchmarked to see how reliable it is as an AGN tracer. We have a lot of tools at our disposal. This is something I've stolen from the CDMS database in Köln. May not have been the recent one, but more than 60 extragalactic molecules have been detected so far, and more keep coming as Alma keeps working. So this field of using molecular lines as tools is expanding now dramatically, quickly. So how can we then use these molecules to probe the dusty nuclei? Well, there's a mounting evidence now that the dusty structures that surround the growing black holes, the dusty torus, that we're moving away from a picture of this thin torus into a more dynamic and complex picture of what it looks like. Here's a cartoon I stole from a paper by Takuma Izumi on the Circinus galaxies. And it basically shows an idea on what these obscuring structures. Here we have the size scales going from sub-parsec to few up to 10 parsecs up here. And it shows, at least this cartoon suggests this very complex structure where we have a dynamical torus, not a static torus, but a dynamical torus which is defined by a balance between inflowing gas and outflowing structures. They're also linked through these failed structures in almost like a fountain-like structure. This very dynamic torus that obscures, feeds the black hole can be probed in molecular lines and or millimeter, submillimeter continuum. And I think perhaps the most famous example of this is the nearby Seaford galaxy NGC1068. Here it is. This is a very busy slide, and the reason for that is because this is a very busy field. What we have here is high resolution, 0.06 arcsecond Alma observations at 450 microns, which revealed the torus. It was actually one of the first times the torus was imaged in the millimeter, submillimeter field. And it revealed this 3.5 parsec dusty, very turbulent torus, again, very dynamic torus, with a gas mass of 10 to the 5 solar masses. It is probably more massive than that, recent studies suggest, but maybe by a factor of few. And it shows this diagnostic line ratio that I talked about before that we think could perhaps work as an AGN tracer. But it shows these line ratio varying quite strongly as we get closer to the nucleus with high resolution. These line ratios behaving in perhaps somewhat unexpected ways for a tracer. So what it is tracing now with high resolution observations is not clear. The idea was that it would be tracing the X-rays coming from the AGN. But what we're now learning, it's probably more linked to the dynamical impact of the outflow on the surrounding gas. So again, we're just at the very beginning of exploring the usage of this line ratio. Now, Alma can provide us with even higher resolution observations. Now we're down to 0.02 arcseconds. So we're now down to parsec scales that we can image the obscuring gas and dust surrounding the AGN. And again, the picture becomes even more complex. There's apparent counter-rotation. This counter-rotation can be real, but or it can be an effect of an inflow or an outflowing torus. So various teams are working on this with different models, but one thing they do agree on is that this torus, again, it's not a static structure. It's a very complex, very dynamic and very evolving structure that obscures and feeds the supermassive black hole. Now, the Alma observations reveal column densities of H2 derived from the molecular gas and derived from the dust observations of a few times 10 to the 23 per square centimeter on scales of a couple of parsecs. Now, this is high, but it's not high enough to explain why this object is a Compton thick. And this is probably because we need to get even closer to the black hole to reveal, to get the high enough column densities to explain the X-ray observations. So even though this is an obscured object, the obscuration is on small sub-parsec scales. What about objects that are even more obscured on larger scales? And now we're getting to the cons. So what we found is that there is a population of what we called compact obscured nuclei that have column densities in excess of 10 to the 25 on scales greater than a parsec. And in our case, scales greater than even a few parsecs. We found that some ULIRGs harbor cons, actually, I'm going to show very soon that it could be as many as 40% of the ultraluminous and luminous infrared galaxies may harbor these cons. They have not been discovered before. We needed actually to get very high resolution and very sensitive observations in the millimeter and submillimeter to reveal them. So they're quite common. And they represent an obscured phase that's been unexplored so far. These objects appear to be quite normal in their dust SEDs, but they have these extreme column density cores, which may provide as much as 50% of the global luminosity of the whole galaxy. I'm going to give you an example here. This is NGC1068. We see here it's actually quite boring looking object. That's also one thing they have in common, as we shall see. Optically, they look quite dull unless you look very carefully. But when we get close to them and observe them in the millimeter and submillimeter, what we've discovered was that this core, this is the continuum image of this galaxy and at 345 gigahertz, a core which is optically thick at 860 microns, which suggests a column density in excess of 10 to the 25. Why do we care? Because basically all of the luminosity in the infrared, this galaxy, is coming from this core, which is has a radius of less than 20 parsecs. We can compare that to the central molecular zone of the Milky Way. This is an image I stole from a paper by Martin from 2004. It basically shows the inner 450 parsecs of the galaxy, which has a mass in molecules on the scale of 450 parsecs of a few times 10 to the 7 solar masses. Now in 4418, twice that mass has been squeezed together in a radius of 20 parsecs. We do not have anything that is similar to this in our galaxy. And we would have thought that these structures would be quite uncommon, but they are not. So how can we trace them? How can we detect them? At these column densities, it gets very difficult to detect them in X-rays, unless we're lucky and we can see some emission coming out, for example, along the polar from the disk. Even in the mid-infrared, now in the beginning I talked about the importance of using mid-infrared as detecting, for example, buried AGNs. But these objects would be obscured also in the mid-infrared. So what we have to do is we have to use proxy molecules. And here I've shown an example. This is HCN. And what we have here is the usual rotational ladder. And then we have the vibrational ladder, which is excited as the molecule absorbs mid-infrared emission. It can then re-emit this absorbed emission at longer wavelengths, for example, in the millimeter, but also at centimeter wavelengths. Then we can detect these lines with Alma, for example. And this is a way to use the molecules as proxies of buried mid-infrared emission that we actually cannot directly detect within mid-infrared techniques. So we're using the HCN as a proxy. And here's an example of one of my new pet galaxies, IC860. Again, quite unassuming looking. There's an image taken with an optical telescope, the NOT telescope. Here we see the dust structure here. So we know that something is going on in the center of this galaxy. But when we observe it in the millimeter. It's SED, it's infrared SED looks quite normal for a fairly normal star-forming galaxy. But when we look at it with high resolution, in this case with Alma, what we find is that the lines that we usually use to probe dense gas, remember I said that AGN is a good tracer of dense 10 to the 4 per cubic centimeter gas. What we find is that these lines cannot actually get to the center. The column densities are so high that these lines become self-absorbed. So we cannot probe the core using these lines. But then we can use the vibrationally excited AGN. So again, remember the ladder, and we are observing then the emission coming from this very highly excited ladder. And then what we see here is the very core here. That even the center of this vibrationally excited line is suppressed in the core. But we're now looking at scales that are inside this hole that we see here. So very small scales, around 14 parsecs. The vibrationally excited emission is coming from hot dust inside a very opaque nucleus. It's actually the case that the millimeter, even at 1 millimeter, we have opacity issues in the emission. So we have optically thick dust emission at wavelengths of 1 millimeter. We have gas densities exceeding 10 to the 7 per cubic centimeter in the inner 4.5 parsecs. And the column density we estimate assuming standard gas to dust ratio. Now this could be completely wrong. So, but if we assume that, we end up with column densities in excess of 10 to the 26 per square centimeter. These are basically brick walls. This is not the only place where it's been found. A similar core has been found in ultra-luminous infrared galaxy with a luminosity of 10 to the 12 in Arctic 20 by Nick Scoville in Sakamoto. So these column densities are huge, and they impact the global behavior of these of the molecules. So what's going on in here? What's hidden inside here? What can cause the opacities in the millimeter to be, I mean, the dust emission to be optically thick? Such a high surface brightness source here, we're talking about brightness temperature over 250 Kelvin in the millimeter to be lurking in here. And we have basically two scenarios. Either we're looking at a fast accreting black hole, and it's possible that the black hole mass is undermassive for its expected compared to the mass of the host galaxy. And or we're looking at a starburst consisting only of massive O stars. There is no room for a normal saltpeter IMF here because we can measure the dynamical mass, so we cannot fit the stars in, no matter how much we try. So these are the two scenarios that we currently are working with. And again, just as we saw in the more normal tori surrounding a black hole, this CON region, the compact obscured nucleus here, is also extremely dynamically active. We see massive inflows towards the centers of galaxies. And we see the inflows in the self-absorption structure of the emission lines of HCN80+, for example. On top of that, in the layered structure underneath the inflow, we see outflow. And the outflow is not revealed until we start to look at longer wavelengths. So we have a structure where the inflow to some degree is obscuring a very compact and very dense outflow. Quite high velocity, up to 300 kilometers per second outflow, but it's not revealed until we go to the longer wavelengths and quite exotic molecules such as methanamine. So what's going on here? Well, and how can we find out? And what is the dust to gas ratio in this extreme environment? Again, we have assumed a normal dust to gas ratio to estimate the column densities. But we don't know yet if this is an assumption that is wrong. And also we don't know if it's in which direction this assumption is wrong. And we're trying to figure out how we're going to determine the dust properties. Now, a mystery of these objects as well is that although we have this huge column density of 10 to the 26, we can still observe the mid-infrared AGN absorption lines towards them. So currently we're trying to piece together a disk outflow system and a radiator transfer structure that would allow both of these things to be true at the same time. How common are cons? Well, we started the Alma CONquest survey, a deep survey of 38 nearby ultraluminous infrared galaxies, luminous infrared galaxies, and also objects of lower luminosity. We looked for the HCN, HCO+, HOC+, and the vibrationally sided HCN, and the continuum. And what we found, and this is just one of the first papers, is just now out by my postdoc Niklas Falstad, where we can conclude that 38% of the ultraluminous galaxies we surveyed and a bit more than 20% in the luminous infrared galaxies have these con cores. So they're quite common in these luminous dusty objects. As we moved down in luminosity, we didn't find a single one. So something happens as we move from 10 to the 10 to 10 to the 11 in luminosity. And it's not clear why this is the case. We found them in major mergers in the ULIRGs and the minor mergers possibly in the LIRGs. So there's a connection to their interaction history that we're still exploring. Basically, all the cons turn out to have dusty outflows, but in a bit of a surprising way. Because when these objects were surveyed in the far infrared for outflows, none were found. One used here's the ratio between the HCN, vibrationally sided HCN luminosity over infrared luminosity. And this is basically a measure of whether they have cons or not. So when they're here, they have cons. This is the velocity of the outflows as measured in the far infrared using the OH, 119 OH line. These objects do not have outflows as detected in the far infrared. The cons tend not to have outflows. We have to go to lower obscurations to find the outflow objects. So the reason for this, we first thought, was because the outflows are compact or not there, that this is an evolutionary effect and we don't have the outflows at all in these objects. Now this turned out to be wrong. The cons do have outflows, they're just not detectable in the OH in the far infrared. Instead, what we're doing is that we looked for them at longer wavelengths with CO, and then we detect the outflows, and the outflows can be quite fast. So let's see, am I going to skip this? So why do we care about outflows? Well, we need to understand the outflows because the nuclear activity will often drive this mechanical feedback, as I said, in the forms of winds, jets, and outflows. And they are important to understand because they help to prevent overgrowth of massive galaxies. They can partially explain the red and dead properties of ellipticals, and they regulate the black hole growth and link it to the host galaxy through the Magorian relation, possibly. And the molecular outflows are important because there's mounting evidence that the gas in the outflow is common, molecular gas in outflow is common, and often that it dominates the mass and momentum flux. So the molecular phase of the outflows are extremely important to understand galaxies evolution. So what about outflows in the compact obscure nuclei? Well, they first seemed like we didn't have them, but then when we started to image them in the CO, we started to detect them. I think one of the most spectacular examples is ARC-220 here. Now, ARC-220 is an ultraluminous infrared galaxy that did not show a very strong outflow component in the far infrared OH absorption line. But when we imaged it, not in CO, but in HCN, remember HCN is the dense gas tracer, we found this collimated structure. This outflow is incredibly dense, and also the outflow in itself has opaque dust. So there's something extreme going on in these galaxies, where the base of the outflow is so dusty that it's opaque even down to millimeter wavelengths as well. The velocity, the estimated velocity of this outflow is 850 kilometers per second. So it's a fast, very dusty, extremely massive molecular outflow coming out from all these extremely obscured objects. The surprise with this, not only that we detected it in HCN, but also that it's not wide angle. So what is suggested normally for these luminous infrared galaxies is that the outflows are wide angle, radiation pressure driven wide angle outflows. But these outflows seems to be more collimated, and it's not at all clear what their driving mechanisms are. Could be radiation pressure, could be supernovae, but it's not clear what's driving out the gas here. Another example here is Zw049. Again, no detection of an outflow in the far infrared. But when we looked at the same molecule, but at centimeter wavelength, we saw a very fast 400 kilometers per second. This is a LIRGs, so 400 kilometers per second is fast. Then we saw the outflow very clearly. So it's obscured or not visible at shorter wavelengths, but it becomes very clear at longer wavelengths. So I wanted to conclude this presentation with one of my favorite galaxies, NGC1068. This is the ugly duckling in the sky, because again, here we look at it in the optical, it's quite dull looking. Even though when we go deep, this is work which is led by J. Gallagher, or we're looking deep at these objects in the HST. We do see that it has some interesting dust structure as we go deep. But it's a small lenticular galaxy. It's not a LIRG in this case. It has a luminosity of only a few times 10 to the 9. But it is the most radio quiet object in the sky. It has deep silicate absorption features, so it's very dusty. But what's powering its infrared luminosity is a mystery, or has been a mystery. Is it an obscured AGN or a very young starburst? It has been suggested that the starburst in that case would be less than 1 or 2 mega years, so it would be very young. When we looked at this object with Alma, we had a massive surprise. And that we found a molecular jet. Now, this is the most radio quiet object on the sky. It does not have a radio jet. But we found it in very collimated molecular outflow. So what we see in grayscale here is the low velocity emission, and this is the high velocity emission. But on top of all of this, we found these velocity reversals along the axis of the jet. So we went from blue here to red, and then from red to blue. And this is a simple model that we put together of a precessing jet, basically a jet going like this. So if the jet is swirling, it would have this dynamical signature exactly like this. So the shock here is not just that there is a molecular jet, but also that it appears to be precessing. We looked at it again with Alma at higher resolution, 50 milliarcseconds, which in this case is 5 parsecs, CO 6 to 5, so we looked at it higher J lines. This is actually 4 minutes worth of on-source data that we published, which is quite shocking. It was not easy to work with these data, let me tell you. But what we found is this very dense and warm gas at the very base of the jet, but just at the very beginning of the jet. We have an incredibly strong excitation gradient along the jet, where we quickly lose emission from the higher J transitions of CO. So it tells us that something really energetic is happening in the very center, but that it quickly drops off along the jet. And this is what we found when we looked at this object with a spatial resolution of 2 parsecs or 20 milliarcsecond resolution with Alma. And it's a spectacular image because I showed it to a colleague of mine, unsuspecting colleague. And he said to me, "Oh, so you finally come to your senses and decided to look at protostars." I said, no, this is not a protostar. This is the center of a galaxy. So what we have here is the stellar disk. We have this incredibly dusty nucleus. We have a narrow wind surrounding a very collimated, but completely radio quiet molecular jet. The size or the width of this jet is only a few parsecs in molecules. And again, we see the velocity reversals, and we also see how the emission is deviating from the jet axis and then comes back again when it reaches its extreme velocities. Again, that is consistent with the notion of a precessing jet. So when we looked at the dynamics, again, with Alma, of both of the jet and its surrounding structures, we found that the emission around the jet itself is rotating. So we have rotation around the jet. So the wind is rotating around it in a fashion that we expect from a magneto-centrifugally driven jet. So we seem to have a combination of a structure which is magneto-centrifugally driven, which could be done, for example, by inflow, and on top of that, precession, which can be caused, for example, by an uneven inflow structure onto the central object. The jet itself is launched inside 0.4 parsecs. So if there's rotation in the jet itself, it cannot be detected. The momentum fluxes of these structures are clearly beyond or too much from what we would expect if this was powered by star formation. So what we're seeing here is evidence of feedback caused by an accreting supermassive black hole and likely not star formation. But the feedback itself is not because there's a radio jet driving out the gas and turning off the growth of black hole. What we could be seeing is instead a feedback, a magneto-centrifugally driven jet, which is helping the gas to accrete onto the black hole. So I'm going to get close to the end. So NGC1068 is an obscured object, but it's not as obscured as the CONs. But if we take the structure, a gas mass in the jet and in the wind, we would easily arrive to the same obscuration levels as we would in a CON object. The columnar densities are high, 10 to the 24. So this is definitely a Compton thick object, but it is less extreme than a CON. When we measure the black hole mass, which we can do because we have the high enough resolution, what we're finding is that the black hole appears to be slightly overmassive. So what we suggest that we're seeing in 1377 is that we have a feeding cycle where the outflow, the jet, removes angular momentum from the gas, allowing the gas to accrete onto the black hole. Most of the mass is carried out, or the inflowing mass is carried out again by the outflow. It loses angular momentum, so it can fall back again quite easily to help feed the black hole. When we compare 1377 to objects where we have a radio jet, which is pushing on the gas, we see some clear distinctions. The objects that have radio jets always have the molecular gas lining the radio jet itself. It's not found on the jet spine, as we see in 1377, and also we begin to suspect that we're seeing also in the CON galaxies for the collimated outflows. So there's a distinct difference between the radio-quiet molecular jets and the molecular gas being carried out by the radio jets. Also, what all of these objects have in common is that the radio jets are pushing the gas often through the disk of a galaxy, while the molecular jet from the XCON and the galaxy NGC1068 is perpendicular to the disk of the galaxy. So these are very likely two very different phenomena appearing at two different stages in the evolution of the galaxy and the evolution of the nuclear growth. So, I hope I've convinced you that dusty luminous infrared galaxies are the hothouses of evolution. They host embedded regions of rapid evolution, and we need to understand them in order to understand the most active stages of nuclear and host galaxy growth of galaxies in general. We can use molecules as probes of the properties of the gas of the growing black holes and stellar populations, because not only can they probe behind the dusty veils, but we can also use them to piece together very complex, to get very complex information, both on the chemistry, but also on the physical conditions of the gas, and also the impact the activity has on its surrounding gas. So the molecules are an incredibly important and useful tool to understand galaxy evolution. Most growing black holes, the AGNs, active galactic nuclei, are obscured. And with Alma, as I've shown you with 1068, we can now resolve the dusty and complex and dynamical tori that both obscure the black hole and feeds it. The most extreme regions of obscured nuclei are the CONs, the compact obscured nuclei. They have column densities of H2 in excess of 10 to the 25, up to 10 to the 26 we found now, on larger scales, on scales of tens of parsecs. We thought they were uncommon, but if we look at luminous infrared galaxies, they're quite common, and there seem to be a luminosity dependence in their occurrence. So ULIRGs, as many as 40% of the ULIRGs may host these CONs, which can contribute 30 to 50 to 100% of the luminosity. So they are very important for the whole luminosity of the galaxy. We use vibrationally excited in emission to probe them. Be careful with the SEDs though, because the mid-infrared is obscured. So we need, again, to use the molecules to probe it. What's powering the CONs? Well, we looked at one very carefully, and I was really, really hoping that with the massive, fantastic resolution offered by Alma that we could tell, but we are now just trying to distinguish between either an extremely top-heavy IMF starburst, there's no room for low-mass stars in this starburst, or an black hole that's accreting close to Eddington. The CONs have collimated molecular outflows that are obscured in the infrared. We need to go the longer wavelengths to detect them. The fact that they're collimated is a bit surprising and not expected if they're radiation pressure driven. A possible example of what could be going on is NGC 1377, where the collimated, extremely collimated outflow is not radiation pressure driven, by magnetocentrifugal driven by an inflow. It's possible that with 1377, we're looking at a new form of feedback where the outflow in itself is actually helping the black hole to grow. Thank you.
Thank you very much, Susanne, for this really fascinating talk with these amazing observations. I mean, let's thank you. I really would like to ask you some questions, but I mean, I throw the questions open to the floor. So if anybody would like to put their hands up, please do so now. Okay, Caroline Bentame.
Hi, thank you very much for this really nice talk. I really liked the HCN maps that you showed from your 2019 paper, where you mentioned that you found this really massive inflow, and then the outflow is only revealed at with a more exotic molecule. How do we actually know with HCN whether we are looking at an inflow or whether it could also be any outflow?
Oh, that's a great question. Thank you for that. So in this case, we could use the vibrationally excited HCN emission to get an idea on the nuclear dynamics. So we really knew what the nuclear dynamics was, and we can get the systemic velocity. So what we could see then was that the HCN 3-2, for example, is redshifted from that. Mm-hmm. So we see that it's an inflow. Now, one has to be careful. If Françoise Combe with her, she would go like this. No, she never would do that. But she would say, well, because being sure that the inflow is really reaching to the center is not just an effect. For example, we could have a situation where we have a bar flow. So the only thing we can say is non-circular motion is not an outflow, as redshifted. So that's usually interpreted as an inflow. But your question is really good, because to be absolutely sure requires more modeling than we've done. The outflow we're seeing, that's in a way easier because we can see the blue shifted. So the emission, the lines suddenly became, the absorption structure become blue shifted. And we can also map them out in their structure. In the case of methanamine, we actually see it only along the minor axis. I'm still shocked about the methanamine. First of all, to detect this complex molecule, and it's so bright, and also to see how it behaves dynamically is something that we did not expect at all, really. Also, the methanamine has really broad lines along the minor axis. So our model suggests that we're having a fairly chubby outflow, which is probably quite wide angle compared to what we expect compared to the other cons. So we had to sort of model these lines, emission absorption lines together to figure it out.
Okay. Thanks. Okay, does that answer your question? I guess so.
Oh yes, thank you very much.
Okay, next question from Ralph Klessen.
Yes, very nice talk, fantastic observations. Lots of thought for thinking, lots of food for thinking, I wanted to say. My question is, since these are very bright, do you have polarization measurements? Do you have any indications of what the magnetic field strength and structure might be in these objects?
I laugh because we put in a proposal now to. So the problem is that the opacities of the dust are very high. Well, that means that you lose the polarization signal. You need to be at tau 1-ish in order to get the dust polarization. And the problem is that if you're at 345 gigahertz, for example, we know the opacities are higher. So we're going to quench the polarization signal in the dust.
Okay.
But one of our really brilliant students has done a model of the vibration line. So we're going to try to use polarization of the vibrationally excited AGN. I don't know if anyone's the reviewer of that, you know, I'm sorry, but to try and, because the estimates, since the vibrationally excited AGN is excited by the radiation field, it becomes very susceptible to, and the radiation field, if this is a disk outflow system, would be asymmetrically illuminating the molecules. Then we should see a strong polarization signal. It could be as strong, I think, I don't remember exactly, but depending on the orientation and structure and the shape of the radiation field, we can have very strong signals up to 20%.
Okay. That certainly would be very interesting.
I fully agree. I hope whoever reviews this proposal also agrees. These are extremely hard observations. We're going to try that on a different galaxy than this one to see. Because going back to Caroline's brilliant question about the inflow and the outflow, it's not, in this object, it's not extremely easy because we cannot really show this beautiful outflow like we can, for example, in ARC220 or in Zw049. We just looked at Merlin data on the OH megamaser, and we can see the outflow, the collimated outflow, really beautifully in the OH megamaser. This is something that Willem Baan said already in 1989, and we can prove that he was right. So that's a very clear-cut case. This one is more difficult because of the layered inflow and outflow structures, which is a real pain. So even though I was sort of hand waving to your question, Caroline, as well, but it's really hard on this object to separate the two. So if you have any ideas, I'm very happy to receive them. But Ralph, did you have any more questions?
No, that was my most pressing one. Thanks. It would be cool to get these observations done.
I should say that there's going to be opportunity to discuss further on these and other issues after the end of the colloquium, because
I don't have a life, so I'm going to hang around.
Offered to hang around, yeah. I don't see any more questions. Let me ask one question about NGC 4418, that was your first con, is that right?
Well, it turns out we thought that was a classic, but that one is different than the others, it turns out, because it does not show. So what we're seeing when we're looking at the cons that we've discovered now is that they all have this suppression of the mid-infrared. So they have this unusual combination. Yeah. So they have high 60 to 100 micron ratios, but low 25 to 60.
Right. I mean, my question is, I mean, first of all, what is the gas density in that object? I mean, the volume density of the gas.
10 to the 7.
Okay, so your grains will be in thermodynamic equilibrium with the gas.
Oh yes, absolutely.
So you know, from the lines you can get the gas temperature, I guess. Is that possible? And
look, I can get the gas. Yes, I can get the gas temperature on the lines, but I can also I can see that they are this. And this is also a problem, right? Because the vibrationally excited AGN is pumped by the mid-infrared at 14 microns. But that's in general equilibrium with everything else around it because the densities are so high. So that means that we lose the signal toward the very core. Remember, even in the vibrationally excited AGN here, you see we lose the signal towards the core.
Yeah.
This is because everything just becomes one temperature. At least that's what we think.
Right.
So it's a pain.
Right. Okay, but I guess your models show, I mean, you can still get some idea about the gas temperature, presumably, right, in this system.
Yeah, it should be the same as a dust temperature in this region. So about 250 Kelvin.
My other question is, you know, you only have these dust measurements at these resolutions at the long on the Rayleigh side of the dust emission. So can you be sure that your mid-infrared observations really are from the same source? I mean, is that I mean, maybe that's an observational question.
So we can. It's a great question, right? Because so first of all, so we can measure. We've measured multiple millimeter lines, a millimeter continuum, a submillimeter continuum. So we need to figure out that at 1 millimeter, basically all the emission is dust. And to be sure of that, we had to make sure we got Q-band data with Alma, so at 45 gigahertz. We need to make sure so we could exclude a free contribution, for example, to the millimeter.
Yeah.
Right. So once we've done that, we measure the surface brightness temperature directly here. So we know that the 250 Kelvin is the dust temperature just from the surface brightness temperature at millimeter wavelengths.
Okay.
From that, we can predict what mid-infrared emission we would expect from that.
Yeah.
We're seeing maybe 2 orders of magnitude too little.
Ah.
And that's probably because, you have layers of dust on top of this.
Yeah, or you've got some structure in there of some kind. All right, well, maybe that's a topic for further discussion.
Yeah, because the mystery is we do detect the HCN 14 micron absorption lines in the mid-infrared. How on earth can we do that?
All right.
Radio scattering should not work now.
Let's talk about that in 2 or 3 minutes. And amongst other things, I don't see any more questions for the moment. So before we thank Susanne, I'd like to make a couple of announcements. First of all, that we will have that discussion session after the end of the formal colloquium. But also, if I may just get the screen back, I'd like to announce next week's colloquium. So I go to the screen share. My desktop, yeah, and put this up here. So next week we'll have a local speaker, Dominika Wejela-Zadek, who's actually going to be talking on a closely related topic, but instead of looking very detailed in the submillimeter, we'll be having more emphasis on the demographics of sources over a large range of redshifts, and we look forward to that next week. So it just remains for me now to ask everybody to put their videos on and put their acoustics on, and let's thank Susanne for this very thought-provoking, interesting talk. Thank you.